Okay, we'll start with this notion of overlap, which we defined last time. Where x and y are strings, the way we defined it is the length of the largest proper suffix of x that is the prefix of y. Okay, and so the problem we want to look at using suffix trees is that you are given a sequence of bunch of strings. I want to find pairwise overlaps. Okay, sometimes you are interested only in the length, but often you are interested in also that string which witnesses that length. So before we talk about algorithm for finding this, let me give you a motivation of for where this notion comes up. I mean, it comes up in various biological problems as well, but let's see some area where it comes up. Remember, what is the first algorithm we saw for pattern matching? Given a pattern, I give you this pattern in advance. Now I want to check whether it appears in multiple different texts. So what did you do? Pre-processing on the pattern. What did we do? What was the pre-processing we did? Yeah, we constructed a DFA of all strings that will be accepted by this DFA is all the strings that has this string as the pattern, right? Say suppose your pattern is AB AB. Can you close that door? How does the automaton look like? How do we, let's see how we construct this automaton that's going to accept all strings that has AB ABA, right? So it will have 0, 1, 2, 3, 4 different states. So when I see an A, I go here, B, A, one more state actually. And this is going to be an accept state. Let's try and fill up the rest of the transitions, right? So if you are in 0, when you see A, what do? When I see an A here, I go here. When I see a B, stay there, right? And here when I see an A, stay there. And when we see a B here, go to 0, right? When I see an A here, because I've seen A, B, and I'm hoping that I'm going to see this pattern, but suddenly I see a B, then I go all the way back. Okay. Now we'll come to exactly how you figure it out, but let's fill this example first. So when you see a B, you start all over because I've made a false positive, there is no string, I'm going to start all over. When I see an A here, go to state 1 because I see A, B, A, and I'm expecting a B. B did not come through. I actually saw an A, which means that I have seen one symbol of my pattern now because my pattern starts with A. So I could go to state 1 if I see a B. Okay. And when you see an B here, Okay, so it's AB, AB, B I am seeing. I go all the way to the beginning, right? And I don't stop here because I am going to capture all occurrences of the pattern. So, when I see an A here, what do I do? So, I have got an AB, AB, A. Now, I see an A, 1 because I have got one character of my pattern, and if I see a B, sorry, 5 on A, don't you go to 3, okay. Okay, 5 on B, what do you do? When I see a B, where do I go? 4, right? And I see a B, then you can figure out that I have actually seen A, B, A, B, so I can go to 4. Now, let us see how do I figure this out. Let us say the transition function at 5, when I see a B, where do I go? I claim the following. So, if I am in 5, what does that mean? I have seen AB, ABA, that is why I am here, right. So, this is equal to overlap of AB, AB, A, B with my pattern. Okay. Stare at the definition of overlap. I am saying I have seen AB, AB, A, now I am seeing B. So, this is all I have seen, right. What is the largest suffix of this, which is the prefix of the pattern? What is the largest proper suffix of this, which is the prefix of the pattern? Well, that is actually AB, AB. So, that means I have already seen 4 symbols. So, I go to 4. Okay. This is actually true everywhere. If you let us go and verify this for delta 3 B, right. When I am in state 3 and I am seeing B, then I claim it is overlap of, I am in state 3. So, I have seen ABA, now I am seeing B, do that with pattern. If I did not make a mistake, then 3 to 1 should be A, okay, because with B you are going here. So, this is A. So, A. So, what is the largest proper suffix of this substring, which is a prefix of the pattern? Well, A is only 1. So, length 1. So, I go to 1. Okay. Let us try delta 3 B, right. I claim this is overlap of, let us write down this. ABA is what I have seen with the pattern. In this case 4 is where I am going. Okay, so in this case I am actually not looking for a proper suffix necessarily. Okay. So, this is actually a generalized overlap. Okay, so let me so if I ask for generalized, then I am just looking for largest suffix, that is a prefix. So, why in this case the largest suffix AB is a prefix of the pattern, and so it is 4. Okay. So, you can verify actually that the computation of the transition function. So, because in general the pre-processing time is the same as the time to construct this automaton, and the major work is in computing this transition function. And it turns out if I am in a state and I see a symbol, where do I go, corresponds to just computing certain overlaps. Okay. So, that is why so this is an area where overlap comes up naturally, and we also saw last time that a brute force way of computing overlap of X. Right. So, I have the string X I want to compute the overlap. I am going to start testing from here and see whether whether that matches with this. If so, my overlap length is n minus 1. If it does not work, I just move here and so on. Okay. So, it is like an n square time. Okay. So, let us get to this problem of computing. Okay. So, you can verify this. There is a general theorem one can write that in this automaton delta of a state I and you see a symbol A, where would you go? Well, it is just the length of the overlap of that string concatenated with whatever that symbol is with your original pattern. Okay. So, now the problem I want to look at is given strings T1, T2, Tn, compute the overlap of Ti, Tj for all I less than j. Basically, or I can even say I not equal to j. Every pair I want to find the overlaps. So, if summation Ti, let us say let's call this summation length of this Ti is n. So, if each Ti is roughly if they are all of the same length, then the brute force algorithm for a pair, the number of pairs is again n square, this is order n square. And using suffix trees, we want to improve this algorithm running time to something like n log n plus something. Okay. So, remember we did using suffix trees, we computed the longest common substring across many strings. The first step was to compute this generalized suffix tree, which just puts all these strings together with some delimiters, and we construct this one big suffix tree which has all the suffixes of each of the strings. So, that is first thing we will do. Okay. So, let me write here. So we will add these delimiters, construct this big suffix tree. Okay, then I am going to compute, we will get to the detail of how you compute. For every node, so again recall what we did for longest common substring. We just said for every node I note down the leaves this subtree contains, which are all the strings where this prefix is appearing, right. We noted this, and then we said we went through the entire set of nodes and found that node which sees all the strings 1 to n and which has the largest depth. So that is the longest common substring, because that is the string of largest length that appears in every string. Okay. So similarly, we are going to compute some information at every node here, and then we will find some largest, smallest something. But here we are going to compute, I mean we will run a for loop, we are going to have a overlap of one string with everybody else, okay, and run through every string. So before that I am going to compute for every node x, compute L of x, which is equal to, okay, this is contained in 1 to up to n, where there is an edge labeled delta I at x. Okay. So here is my internal node x. It's going to have a lot of edges. Maybe some, delta I will end here. Delta I's are always at the leaves actually, by the way. So if it ends here, then I am going to put I in this set, L of x. Okay, we'll run an example. Okay, now I am going to have a for loop. So what is L of, an I in L of x means what? Let's capture that information. Okay, so as an aside, implies what? Right. So sort of I ends here at this point. What does that mean? What I mean, in a suffix tree, there is a node which just branches off to delta I and stops. What does that? What does it say anything about that part of the string? It's a suffix of ti. That's all I'm asking for. Yes, which means that the path label x. This is the notation we used. Right. This string all the way from here. This is what I call, you concatenate all the characters here. That's the path label x is the suffix of the string ti. Okay. So now I am going to run through for j. Okay. So let's see. I mean the proof will be clear if you keep observing this for. For j equal to 1 to n, x is r, while x is not equal to a leaf, for every I in Lx, update overlap of I and j 2 depth of x. Yeah. Okay, since I am looking for a proper substring, because I am looking for overlap, not generalized overlap, if depth of x is less than min of the child of x following the next symbol of Tj. Okay, there are a lot of notations and it might sound mysterious here, but it's not very hard at all. I'll just explain what's going on here. I'm computing overlap of Ti and Tj actually. I mean, basically overlap of Tj with everybody else is what I'm computing now. Yeah. So, does anybody already see this? The whole thing? 1, 2, you see this? Okay. Okay. So, we'll go over it slowly, right? So, let's so I compute this generalized suffix tree. Sorry, oh, this is not visible. I'll write it up there. Okay, I'll write it here. So R is the root. On Ti, Tj. And then I move to x. Okay, so this end while and end for. Okay, when I asked does anybody see this, I didn't mean whether you can actually see the board, but whether you see the algorithm's correctness. But I realized that you have to see the board first to see the correctness of the algorithm. Okay, so so what's going on here? I construct this generalized suffix tree, and so I start from a root node. So let's actually do an example. You're making a mistake here. So let's say I have T1 and I'm just going to blindly write down what's here. So think of this concatenated strings. I've just drawn this compact suffix tree for this. So let's just, so you have a suffix a delta 1, b a delta 1, and aba delta 1 is here, aba delta 1. B A B delta 2 and so on and so forth. So you can verify that. So there is B delta 3, yeah. So no, this is BB delta 3, must be B delta 3. Where is B delta 3? So this is delta 2, delta 3, and then B delta 3. Okay. So you can verify that all the suffixes are there for each of the three strings. So there is B delta 3, BB delta 3, A B B delta 3, and A B delta 3 should be somewhere. Okay, so that's another thing that's missing. Yeah. Okay, so this is a generalized compact suffix tree that has all the suffixes of the three strings here, and I am trying to find the overlap between every pair of strings. Okay. So first thing we compute is for every node, which are the delta i's associated with that node. That's very easy to do. I mean, we'll do the running time analysis later, but at this point, node A has delta 1, delta 2, delta 3. This was only 1, and this has 2. This has 1. This is 2 and 3. These are the deltas directly associated with those nodes. Okay. So now let us say I want to compute. So there is a for loop that goes from 1 to n. So I am going to compute the overlap of T1 with everybody else. Okay, the overlap of T1 with T2, T1 with T3. So I am going to follow this T1 suffix here. So at this point, there is a 0 initialization that is happening. T1 with 1, T1 with 2, T1 with 3, these are all 0 at this point. So now I come here. So follow for every, so I start from root, while x is not a leaf. For every I in L of x, I am going to update the Ti Tj. So I am not interested in T1, so I am going to ignore that. So the next is AB, and I am going to say the overlap of T1 with T2, because I am seeing T2 in this node. Overlap of T1, T2 is this length AB. Does that make sense? Actually, it's overlap of T2 with T1. Yeah. Okay, the order is important. So I should say Tj comma Ti. Is that what they say? The little. I think it should be this. So at this point, I am running T1 here, and when I come here and I find a 2, then at this point I say overlap of T2 comma T1 is this length, which is whatever the depth is. That is what the depth of x is 2. And why? Because why is this? So this is a prefix of T1, because I am following through letters of T1. So at any point of node, I am having a prefix of. So this AB is a prefix of T1, okay, and the fact that I am seeing 2 here means that there is a delta 2, which means that this is also a suffix of T2. Okay, so I have a prefix of T1, which is a suffix of T2, which is AB, right. So overlap of T2 T1 is 2, but this may not be the largest. So I am going to keep going down again. That is what happens, right. So I update it now, and then I go to the next symbol of, I am following through J, Tj. So I follow through Tj in this case would be, I am done, T1, sorry. So A, so I come here, now I reach a leaf, so I am done, because I update this only if I am not in a leaf. Okay. So what is happening in one for loop is that for every other I am computing the overlap of Tj with that Ti. I keep updating it. Okay, so there is one while loop which just goes through path of j, and every time when I see some I there, okay. So this is a prefix of Tj, but now you are telling me that whatever I have seen is also a suffix of Ti, so I do some updation. Keep doing it, and every time I am increasing this depth, so I note down this depth of x, and that is my overlap. Okay. Okay, so that is proof of correctness by example, some show of hands and so on. Okay, one can actually formally prove, but this is what is going on here. Is that clear? So now let us just get to details of how do you compute this L of x, and what is the overall running time for computing these overlaps. Okay, that is to make sure that I do not have that this string is a proper whatever suffix or prefix, because the way I defined overlap, generalized overlap, I said I did not even want proper. For an overlap, I want this to be thing, I do not want one of them to be a substring of the other. Okay. So if depth happens to be equal to one of this, that means that one is a substring of that, and I do not want to note that the previous depth was good enough. Okay, that's why. Yeah, thanks. You asked that question. Okay, so let's just quickly do a running time. So this is brute force algorithm. Let's do the running time, right? This last time I said if summation Ti is n, then there are algorithms, we did not see them, but there are algorithms which can compute this generalized suffix tree in order n log n time. And this thing has order n nodes. That's what this compactification does as well. So now we compute L of x. We did very similar to what we did M of x last time. So we just go bottom up, right? All I want to know is, I go through these leaves. Whenever I see a delta I here, I make that value here in this parent. Actually, I can do top down as well. It's not a problem because it's, all I have to do is for every node look at its children and see whether there is a delta I there, and then put that delta I in that set. Okay, so this would be, I would say, for every node, I just have to look at its children. How many children can there be? Right? So because there could be one for each character, there could be one for each delta I. The number of delta i's is capital N. So that's the time for this. Okay, so for step 3 we are going to do some overall analysis for across all for loop. I mean across all execution of the for loop is some order n, summation Ti, right. Each time I start from a road, go to the next symbol of a particular Ti, next symbol of a Ti, and so on and so forth. And so totally summation cardinality Ti is total number of steps, traversing I am going to do. So order n, and each time you may have to look at all your children to figure out where the next symbol is. So I am going to just put a gross estimate of order n times the same thing, sigma plus n. Yeah, and that's it. And then at some points you are just going to change the value of this overlap to something else. If these conditions are satisfied, that's a constant time operation anyway. Yeah, so that's it. And finally you have and you may have to scan through the entire thing to no, it's okay. I mean you will have a table of overlaps, 1 2 up to n, 1 2 up to capital N, sorry. So when this updation happens, you are just changing some entry here, and finally this would be the output. Essentially your running time is n log n plus n into capital N, improving from n square, okay, because earlier it was n into little n. Little n is sum of all the lengths, whereas capital N is the number of strings you have. some improvement there. Okay, any questions? Is that clear? Okay, so the next application of suffix tree is about computing what are called repeats. Okay, many of these actually, the overlaps, longest common subsequence, repeats, all have interesting applications when you look at DNA sequences. Okay, so in fact, suffix trees are earlier, as I said, were largely used for pattern matching, but then there's biological applications through more interesting questions, and they were solved using suffix trees. Okay, so what is a repeat in a string? Repeat is some substring that repeats. Okay, so I mean, you can think of the string A as a repeat because A is repeating at several places. B is a repeat. C is not a repeat. D is not a repeat. AB is a repeat. AB is appearing at several places. BAB is a repeat, but then it's sort of overlapping. So we will call, okay, so let me formally define what is a repeat. If there exists I and j such that ti plus 1 to tm equal to p1 p2 pm, which is actually equal to tj plus 1 to tj plus m. That means in this text there is a location I and there is a location j, and need not be actually disjoint, but let us say for so here is this pattern which appears at both these locations. Okay, and we are actually more interested in what are called maximal repeats, because if you have a repeat, then any substring is also a repeat, right? So I am more interested in a maximal repeat. So what do I need for that? It's a maximal repeat. What do I need? I mean, this P is irrelevant, right? I mean, whatever substring that's repeating is what is a repeat. Okay, I want to call it a maximal repeat if I can't extend it to get a larger repeat, right? So what for that to happen, if Ti is not equal to Tj, and Tm plus 1 is not equal to Tj plus m plus 1. Okay. The next strings are not the same. Okay. Is it clear? So, what are the maximal? So, there may be lots of maximal repeats. What are the maximal repeats in this string? Let us see. Right. AB is appearing at a lot of places. BAB is a maximal repeat. That's probably it. Okay. So, the question you are interested in is you are given a string find all maximal repeats. So, you are going to use suffix trees to is AB a maximal repeat? I thought somebody will ask me that. Yes, for this reason. So, if you take this occurrence of AB and match it with this occurrence of AB, then yes, you can't extend. So, it's a maximal repeat, right? Because there exists I and j is all I care about. I mean, you are right that if I compare it with, if I look at these two, or no, if I look at these two, then yes, I can extend it by a B. So, AB is also maximal repeat.
Then we can call A also as a maximal repeat.
Can we call?
A and the second A.
Yeah, you're right. Yeah, sure. Right. This A and this A, no, this A. Yep. B also? Yeah, I'm sure, right. Right. This B versus this B, maybe, yeah. No, not this B. This B. Because you can't extend it by at either end by whatever is there. Yeah. Okay. So, we are going to compute a suffix tree and then see how maximal repeats are in, how can I identify maximal repeats by looking at the suffix tree. Okay, so here is a claim. So, if X is an internal node, then path label X no, I want to say the other way. Sorry, exactly the opposite. If P is a a maximal repeat of T then there exists an X, an internal node of compact suffix tree of T with so if you have a P which is a maximal repeat, then I claim that there is some node in your compact suffix tree X whose path label is actually P. And why is this? Well, because this P appears in two places, so if you look at the suffix starting at I plus 1, so P will be here and then it goes somewhere and you will have an I plus 1 as a leaf in the suffix tree, because there is this substring P is what the first I plus 1 and then it branches off somewhere, and the suffix starting at I plus 1 leaf will be here, and P also happens to be appearing here. That means if you look at this J plus 1, so that means there is somewhere else you will have J plus 1, right. So this node in your suffix tree will have two different children, and so they will survive as an internal node in your compact suffix tree. Yes, that is an argument. Since it appears in two places in your text, this prefix will have two children at least, and so you will have, this will be an internal node in your compact suffix tree. Okay. Now this may not be a maximal, okay. The fact that it is a maximal repeat also says something more. What does it say? What else do you know? The maximal repeat means that this Ti, whatever the before, is different from Tj. And similarly, you know, whatever Ti plus m plus 1 is different from Tj plus m plus 1. That's what I have. Okay, that's an extra information. Keep that in mind. We'll come to that. But this, you know, that's a proof of this claim, that because this pattern occurs at a couple of places, you take those two suffixes, they'll, you know, have this initial path in the tree and then they branch off. So a corollary of this is that there are at most n minus 1 maximal repeats. Why? We saw that in compact suffix tree there are n leaves and the number of internal nodes is at most n minus 1. I mean, we did some degree analysis, remember, that is how we argued that the total number of nodes is order n. There are n leaves and the remaining nodes is bounded by at most n minus 1. And since maximal repeat corresponds to an internal node, you can have at most n minus 1 maximal repeats in this string. So should I just output every internal node as a maximal repeat, right? I can compute the compact suffix tree. Should I just output every internal node as a maximal repeat? Hmm? Well, there is branching here. That's what an internal node means. I mean, this is only a one way. If it's a maximal repeat, you have a branching because it appears at two places. Now, I just pick some internal node, then can I say that this is a maximal repeat, or where may, how will it fail? How can it fail? Any leaf to the left of it, right of it? Right. Yeah, okay. So you are saying, okay, good point. So you are saying that since these two symbols are different, the starting symbols are different, I can't extend P. That only verifies this condition. I also need this. See, what if this symbol and this symbol are same? Then it's not a maximal repeat. Right? Your observation is that since I am branching here, the next symbol for these two suffixes are different. Good point. But the previous symbols, which means something before this P, which is this and this, meaning the Ti and Tj could be the same. Okay. So I just need to verify that, and then I am almost through. Okay. So all, let's just use that. Okay. So that's the only thing which stops you from just calling any internal node as a maximal repeat. So let's introduce this notion of left diverse. Okay. So let X be a node in the compact suffix tree, right? Let's call left symbol of X is the symbol to the left of, you know, the, I'll write position immediately to the left of path label X. Okay, so what am I saying? Here is my node X, and there is a string P that represents this. A string P is appearing, you know, is representing certain thing in the text. Take this symbol, which is to the immediately to the left of this, and I'm going to call that as the left symbol of X. Okay, so when you think of a node in this suffix tree, it represents a string which occurs in the text. Okay, so it actually refers to a particular appearance of this string in the text. Whatever position to the left, whatever symbol that's appearing is what I'm going to call it as a left symbol. Okay, and an internal node is left diverse if its subtree with two different left symbols. So, I am going to call it a node as left diverse. If I look at the subtree rooted at that node, look at the leaves and see their left symbols. If at least you have two different left symbols there, I am going to call this left diverse. Okay. Now, left diverse nodes are the maximal repeats essentially, because you know, okay, is that clear? Yeah. So, the claim is corresponds to a maximal repeat if X is left diverse. So, let us see why this is, because if you have an internal node, these two symbols are so let us say these two symbols are different, that is why there is a branching going on. But if you have some node here and some node here with two different left symbols, then you are done, because their next symbols are different and they are starting, the symbol before are different. So, what you have is a maximal repeat. And then does not matter if you have this differences here, even then that is fine. So, wherever. So, if you have a subtree, some leaf, two different leaves having two different left symbols, then you have got this is a maximal repeat, because it is branching, it is an internal node, so it is branching. So, the next symbols are different, and you also ensure that the previous symbols are different. So, that ensures these two conditions, Ti is not equal to Tj and this is not equal to, and that is a maximal. So, now algorithmically how do you compute this? So, I have computed this compact suffix tree, and how do I check whether a node is left diverse? Right. So, I have this compact suffix tree, and I want to know for every internal node is it left diverse, which means that in this subtree rooted at that node, do I have two leaves whose immediate left symbols are different? So, bottom up, okay. What do I do? Yeah. So, all I care is whether I have two different symbols or not. I do not even need enough. If I have 10, I do not necessarily need 10, right. Whether they all have the same left symbol or two different is all I care, because that is what left diverse means. Okay. So, you do not even need to store all left symbols. So, you can do something even simpler. Yeah. So, what do I do? So, I look at the leaves here. So, let us look at the parent of a leaf, right. These are all leaves. For for each one of them I look at their left symbol, and if I manage to have two different left symbols, then I just the beauty is that if this is true here, it's true for all its ancestors. So I can just carry this forward, because if this subtree has two leaves with two different starting points, then so does this, because you can just use this subtree. Okay. So these are two different guys, I just write true. If they are all the same, what do I do?
Store that particular symbol in that
Just store that particular symbol. Just false alone is not enough. I mean, I could say false, and but then when I go here and look at this tree, I may have a false here and a false here, but this could still become true, right? How? If these two symbols are different, then I would be true. So what I will store, if all of them have the same previous starting point, I note down that symbol and write that symbol here, whether it's A or a B or a C or something. Similarly, I note that here. Okay, so somewhere I'll have it true. So once one node gets true, it gets propagated all the way up to its parents, ancestors, and otherwise I just note down this symbol, and then I can just, so basically from its children I can just compute what its value is. Okay, so this is like an order n sigma computation. For every node, I just look at its children and get the value up after computing the suffix tree. So suffix trees are really very powerful. If you again look at a string and think of computing all maximal repeats, it does sound, it doesn't sound that easy. Once you have suffix tree, you have lots of information on the nodes, and you can get these, after you construct the suffix tree, couple of traversals of this whole tree, you get to answer a lot of questions on this. Okay, I will end this with just one more data structure which you might just come across, and it's called suffix arrays. They have also been pretty classical and popular. Suffix array is the following. Basically, how many suffixes are there? We already saw. There are n suffixes. Start at a position, go all the way to the end, and that's n suffixes, right? Sort this whole thing lexicographically. Okay, so sort these n suffixes. And output the permutation of the sorted order. That's the suffix array. In other words, let's say your text is then your suffix number 5 is just B, suffix number 4 is AB, suffix 3 is CAB, okay. Now let's sort this lexicographically. So which one comes first? So again, it's useful to have this dollar, and let's assume that dollar is greater than alphabet. So I will have this is the text. Let's get this out of the way. sorry, ABC, AB. So, which one will be the first? This one, right? ABC, AB, because C is smaller than dollar, so this will come first. So, I will have, I mean, some convention we can assume about this dollar symbol anyway. So, I will have 1, then would be 4, because that is another one starting in A, AB. The next one starting in B is 2, and then I will have 5 and 3. Okay, and this is my suffix array. It is just an array of permutation. Okay. So, basically what I have done is I have sorted this. So, that means I have written this as ABC, AB, and then 4 which is AB, 2 which is BC, AB, B, these are all the suffixes, 5 suffixes in sorted order. Now, when I want to search for a pattern, so this is my suffix array. So, the beauty about suffix array is no pointers, nothing, it is just a nice one single array. Okay. You pay for it and you pay for it in the time to search. Okay. So, trying to search for a pattern, I will do binary search. This is a sorted set of strings and I am looking for a string. I know that a pattern exists if it is a prefix of some suffix. So, the pattern is going to appear somewhere. So, I will check there, where is it appearing, right. So, that requires binary search on this sorted string, but so there is log n many comparisons I will make, but each comparison is what? A string matching. I take my pattern, compare it with this suffix. Okay, so, that could take potentially order m time. So, overall order m log n time. Okay. And why is this enough that I do not need to keep the suffixes, but I just keep these numbers. Why is that enough? Because your text is there, right. So, when I want to know the suffix, when I want to do the comparison, go to that text. So, I do a binary search. So, I go and check the middle one, which is 2, which means I go and check the substring starting at position 2 and check for my pattern, and it is going to tell me, oh, you have to go left or right, right, and then I go and come back and do binary searches. So, overall time would be if we just keep only the array, but there are some enhancements to suffix array where you keep some other extra information and you can improve this runtime to m plus log n. Not just the array, but if you keep some other extra information, you can improve this to m plus n log n. Yeah, so this is also another popular data structure for string matching, suffix arrays and suffix trees. There is a lot of work, there are various conferences pretty much talking about string matching. And so, some of the material I picked up is from this book. Let me just give a reference to this. Right. Bioinformatics is this new area where computational problems occurring in biology. Okay. String matching is one kind of problems, but there are also various alignment problems and a whole lot of problems. So, Springer There are also books on computational biology by Dan Gusfield. Gusfield. That's a few years old. You might be able to find them in the library and check them out.